Hi everyone, so this is the first video for our series that discusses kinetic theory of gases. Kinetic theory of gases involve a lot of derivation which can be quite complicated sometimes. So this video serves to lay down the foundation and talk about the concept that we need to derive all these things. So let's get it started. The first concept that we need to know is the concept of change of momentum. So let's write down. So when a particle, a gas particle to be specific, hits a wall, we assume in kinetic theory of gases, we assume all the collisions between the particles and the wall to be elastic. So if we say it's an elastic collision, there's two conditions that need to be abide. So the first condition is the kinetic energy must be conserved. So kinetic energy, we represent it by the symbol of K. Whereas the another thing that need to be conserved is our momentum. Something to take note here is for momentum, we are using capital P instead of small p. So it's different from what you learned in the momentum and impulse chapter earlier. Okay, so it's capital P right now. So let's draw a situation, probably that will help us understand things better. So imagine we have a wall here, a gas particle, and this gas particle it's moving towards the wall. So if it's moving towards the wall, we say that it has an initial velocity. So, and we can say that this gas particle has a mass of m. So now let's try to determine the change of momentum of this particle if it's colliding with the wall elastically. Okay? So the first step that you need to do is you need to find the final velocity. And that would be very important, finding final velocity. So how do you find it? I think it's better that we start with the conservation of kinetic energy first, because that allows us to get the magnitude of the final velocity first. So how do we do it? The sum of kinetic energy initial will be equal to the sum of kinetic energy final. So we know here there are two things involved, two objects involved, the wall and the gas particles. So there will be kinetic energy initial for the particle, and there will be kinetic energy initial for the wall, and of course there will be kinetic energy final for the particle and kinetic energy final for the wall. So now we know that the particle will be moving initially at half mvi squared. Then the wall, it's always rigid. Okay, let's be very clear and write that it's a rigid wall. So rigid wall means by it will not budge, it will not move, so the initial, the final velocity will always stay consistent to be 0. So now we know this will be half m v final square plus 0. So with the situation now, I believe we can do a bit of quick maths here. We can remove this, and since half m here are the same thing, we can just eliminate both sides. Okay, so now you are left with v initial square equals to v final square. So from this equation alone, from this expression alone, we can arrive at a conclusion that v initial and v final, they should have the same number. Okay, so because if you square root something, there's possibility of being positive and negative. But one thing we can know definitely is the magnitude of velocity will be the same for initial and final. So if I put a modular sign, that means it's a magnitude. So magnitude of velocity is basically just speed. Okay, so it means the initial speed and the final speed will be the same, just that they might be in opposite direction. In which, if you look into this diagram here, I believe it's quite intuitive that the final direction will be opposite to the initial direction. So now the next thing that we can do is we can determine the change in velocity right now. Okay, let's write it very clearly. So it's same speed but opposite direction. So if same speed opposite direction, what can we write? Can say that the v initial, if you want to represent it, equals to negative v. Okay, negative because it's moving to the left. So we take left as negative, we take right as positive. It's just a simple sign convention here. So we can see that v final will be just positive v. Okay, let's just keep it simple, represent it with v. So now if you want to find change in momentum, again remember our momentum here will be in capital P. So now if you want to find change in momentum, it will just be equal to P final minus P initial. So let's build it. The P final momentum is just the product of mass and velocity. So it's mvf minus mv initial. Then we substitute in what we write down here, mv minus m negative v. So you put in everything, the answer will be 2mv. Okay, so this is the first concept that you need to know, how to determine the change of momentum of a gas particle when it hits the wall elastically. Means when it hits the wall, then it bounces back. Let's be very clear, it bounces back. Okay, so that's the first concept. Moving on to the second concept. For the second concept, we will learn how to find the force due to this change of momentum. The second thing to learn is find the force from change of momentum. This will be related to the chapter of momentum and impulse. We will basically use the impulse momentum theorem to derive this thing. Okay, so how do we do it? Again, let's write it really clearly. The concept that we will use is impulse momentum theorem. So impulse momentum theorem says that the impulse will be equals to the change in momentum. Okay, the impulse experienced by something will also be equals to the change in momentum experienced by that something. So with that said, we can say this impulse represented by J is just the average force times the duration of time where that event occurs, the duration of that event. Then average force is the average force being exerted on that object across the duration of the event. So this change in momentum will just be delta P, nothing special. So if we shift this around, then the average force will be equal to change of momentum over change of time. Okay, if let's say you want to find how much is the average force exerted by this little particle in our first concept here, this little particle, how much force does it exert when it collides with this rigid wall? We can know that the change in momentum is 2mv, so this will be very useful for our calculation. Just say that it's 2mv over the time of collision, which if you find out, then you are able to find the average force exerted by the gas particle on the wall. This is a single gas particle. Later in our derivation for kinetic theory of gases, we'll be doing it for a lot of particles. Okay, so that's the second concept. The third concept that we are going to learn is how to find pressure due to a force being exerted over a certain area. So let me write it down. So we know just now for that situation we have earlier where a gas particle collides with a wall, probably we can't really talk about the cross-sectional area. The area is really too small to be discussed. But if there's a large amount of particles colliding with the wall over a short period of time, probably the wall itself will be an area. Then the number of particles colliding, you have a total change of momentum, and from that total change of momentum, you can calculate force. Okay, so it's doable to calculate pressure, just that you need to see it as a big picture. You need to see the whole wall with many particles colliding over the short period of time. That you don't worry about it, we will leave it to the next video. So now we just say that for pressure, it will be represented as small p right now. Momentum, capital P. Pressure, small p. So small p, it will be just F, okay, over A. So later it will be A will be the area of the wall, then force will be the force exerted by many particles colliding at a wall within a short amount of time. So that's F over A equals to pressure. The fourth concept that you need to have in the back of your mind is you need to know how to relate speed with kinetic energy. So speed is V with kinetic energy, which is K. So this it's a really relatively simple concept that you learn in work energy and power. So it will be K equals to half mv squared. Nothing special about it. Just to remind you that this formula exists. Okay, so the last concept, the fifth concept, which is the concept that we learned quite recently. You might learn it in chemistry, you might learn it in physics. It's the ideal gas law. So ideal gas law will be PV equals to nRT. So if this is in terms of mole, so if it's in terms of particle, then it's PV NKVT. If this is in terms of particles. Okay, so there are two versions. Both have their own usage, both have their own pros and cons. So you might learn this through chemistry in phases of matter or states of matter, properties of matter, I think. Okay, so for physics, you will learn it to learn about the macroscopic properties of gas, how pressure, how volume and temperature relate to each other. So now we also use this formula to compare the macroscopic picture, the microscopic picture, to gain some relationship. Like what's the relationship between temperature and root mean speed, root mean square speed, or the relationship between the root mean square speed and pressure. So we try to relate macroscopic quantities and microscopic quantities. So these are the 5 concepts that is important for our derivation for kinetic theory of gases later. So that's all for this video. Stay tuned for the next one. Thank you.